minutes earlier. The reason I had like a 30 minutes break, it was because I got confused over the equations and the diagram. It doesn't seem to be right. So I take a look at that, and then I found that the rates here, they are wrong. They are like in the different places. So I was not very consistent. The first picture is this rate, right? But then in the equations, it's actually in this way, in the equations. Okay. So let us look at the state transition diagram and write the transition rate matrix together. Okay. So the state transition diagram here, you have up at state 1, you have derated at state 2, you have down at state 3. So when you write the transition rate matrix, you look at, I always like to write the number so that it keeps in my mind that I'm talking about the rate from which state to which state. So from 1 to 1, we keep it first. 1 to 2, so 1 to 2, you have lambda d, right? Lambda d. And then from 1 to 3, you have lambda, okay? And then from 2 to 1, you have mu d. From 2 to 2, just leave it first. From 2 to 3, you have mu f. Now we are at the same page. And then from 3 to 1, you have mu. From 3 to 2, you have lambda f. Lambda. Okay, so it's the same thing now. The diagonal part is the negative of the summation. So you have minus of lambda d plus lambda, minus of mu f plus mu d, minus of mu plus lambda f, which is the same as given in that transition rate matrix. What that you need, I'm sorry, what you need to change is these two rates, okay? I don't want to change the equations. It will be a lot of work to change the equations, so please change the picture, the diagram. And the intuitive idea that we explained is still the same, okay? So you need to change these two. Now you might have some confusion why we choose to use mu or choose to use lambda. Most of the time we choose lambda to represent the failure rates. We use mu to represent the repair rate. So lambda should be from the better state to worse state. Mu should be from the worst state up to the better state. But there is no differentiation between these two in terms of the representing the transition rate, okay? So there might be the case in some example they use mu to represent from the state that is better to the worst state. That's also possible. It's interchangeably. It's a transition rate. You need to look at it as a transition rate. I can call transition rate A, B, C, D, ก ข ข อะไรก็ได้ whatever that we call it. But essentially, it is a transition rate. Okay? So now things make sense again. So I write this equation, and then we can solve this to find the probability. In the textbooks, they don't have this. Am I right? They don't have. Don't even remember I did that. Can't remember. This slide was made like 10 years ago. It was a long time ago. Okay. So now when we look at the three state, when this is a simplified version. And what we want to know is how we can make, cram these two and then compare it. How do I do that? We look at this. This is our goal. I wanted to simplify to have in this format. So that's why I have have the I have to multiply at the denominator and then the numerator, both of these, which gives me that, right? Okay, why did I do that? I just trying to force this equation to look something like this so that I can see how I can simplify these two state transition diagram. Okay, so reformatting the equations, what we found out is that if mu f is much less than mu d, then it also goes to 0, mu f over mu d, mu f over mu d, okay? And then if lambda f is much less than mu, then lambda f over mu, so this becomes 0, this becomes 0. If these two become 0, then I can, these two will cancel out, right? Right? See that? These two become 0, these cancel out, and these two become 0, and that you just get, that's why you just get this, okay? It will be this approximation, okay? So of all these things, just trying to show you that our intuition should be right, okay? If we are here, and if the system is less likely to change the state directly from derated to downstate than to here, then this one, you shouldn't see it. And the same, when you're right here, and you don't make this transition rate as often as compared to this, then you can simplify it, okay? So that is how to look at the conditions on how we can simplify the transition rate diagram, okay? And then for the independent outage model, it's the same thing that we have it over there, which is a two-stage Markov model, upstate and downstate, okay? And with this two-stage Markov model, if it's independent, we can extend it to a multiple. Now you have seen it quite often. You have 4 states, right? I draw earlier 8 states before. You have 2 components. The thing is, there will be no direct transition. There will be no direct transition right here. You change state one at a time. That's the idea of independent. Okay, change state one at a time. And this is an example of the 4 units. So from 4 units, you're just cascading down from 200 to 150. And 150 can only go to 100. And 100 goes to 50. And 50 goes to 0. Okay? There is no direct transition from 200 to 100 or 200 to 0. So that is independent. That's how you can draw this nice equivalent model. This is what we say by independent model. Change one state at a time. When it comes to dependent outage, what causes it? You have what is called a common cause outage model, component group outage, a station originated outage, cascading outage, environment dependent failure. We'll spend more time on that environment dependent failure. So first, for the common cause outage, you have multiple components, but then it failed at the same time through external cause. Like in this example, lightning strike a transmission line. A transmission line each works fine, but when the lightning strike, it brings the transmission down, both of them. So that is the common cause. Okay. Now the question is, what about why don't we have I got the question last time, why don't we have the transition from both components being down and both going up? Well, if you can fix, if you can spend time, spend your resources, your crew member to fix the component at the same time, then you will have the transition. But most of the time, when we are engineer, when we fix these components, we will spend one component at a time, right? It's more cost, it's more worth the cost that way. So that's why you see the transition as in steps. Fix one first, and then fix number two. And here, you fix number two first, and then you fix number one. Okay. So that's how you see the transitions. Okay. The next one is the component group outage model. The component group outage model looks at the, for example, in a substation. Okay. You have a transformer, you have the load, you have in a bus bar, you have circuit breakers. If one component fails, it leads to other failure to the same group. It could be that the failure happens at the simultaneously. Okay, so in this case, when they explain it in this case, they look at that it doesn't really fail as in it causes a breakdown in each component, but because one circuit breaker trips, the rest of the line that connects to it also goes to failure. Okay, so that is the protective stage of the failure. You will see this kind of a component going up and then it goes down, but there is no more lines coming down here. It doesn't matter whether component 2 is down or not, but the whole system needs to be fixed by fixing this one, right? So this is quite similar to the dependent failure in series network. Actually, the concept is the same. Okay, so this is what we call the component group outage model. Next one, we have, actually this case, it's also quite easy to calculate the probability of each of the component in the steady state, right? You can use the frequency balance. It is the same thing as calculating the probability here. Exactly the same thing, okay? Now, we have the station originated outage. So in this case, you might have the terminal outage of some components in the transmission or the distribution system. So consider if there is a fault, okay? So all the faults, it causes all of these to fail at the beginning. So when the switch 5 opens, then the rest can operate, but some of the components still fail. So when we come up with this kind of model, what you need to understand is, first, what is your system? Second, what are the components in your system? Third, how does it relate when the failure happens? How does it cause the next system? How does it cause the next component to fail? Okay. So when you look at this, you have to look at the failure effects in each of the components so that you can write the state transition diagram correctly for your application. In reliability analysis, they also propose this kind of cascading outage model. So it's a sequential of components in the system. Like in the when there is some rollout, blackouts or brownouts in the network, one loss of the component might cause the other to overload, and then it get the cascading failures. So these are the effects that they represent. But when the actual application, this model is not quite used per se. In the reliability analysis, what I found out is that they focus more on the steady state analysis. In this type of the cascading outage model, you need to look at the transient stability. That is more concerned because transient stability has some the overloading issues, and then you need to trip over some of the components out of your network. Okay, so in this model, it's not quite widely used, but I just represent that, you know, if you have some similar problems that you're working on, then you can look at that and then see how you can use it. This, however, is quite common because it's an environment dependent model. You see that for the lightning areas, for example, throughout the whole year, if you look at your failure data, you will see that during the monsoon or the rainy season, you will have higher chances of the lightning strikes, and the components are likely to fail more as well. So if you use just one model to represent the whole system, it might not be as accurate because you need to factor in the weather, you need to factor in the time of the year of that. So in this environment dependent model, the unit has the different repair and the failure rates. Okay? And within the weather, you have the change of the states of the unit. So you have the normal weather some time of the year, and you have the adverse weather, which is a time that you have a lot of rain, okay, and you have lightnings. So these are weather dependent failure modes. I will go through the explanation in the detail in the example on how we can combine this to give us the equivalent model for the analysis. Okay, so this is the environment dependent model. Okay, I'll go through this quite quickly. The parameter estimation is important for you when you do the research work. It's important because it's how you got the data in to do the, you know, garbage. They always say garbage in, garbage out. It means that if you don't care about the data that you collect and clean it well, then whatever you do when you try to analyze it will not make sense. Okay, so pay attention to your data and then see whether it makes sense first before you use. The accurate analysis depends heavily on data. Okay, and this reliability analysis, you can't avoid collecting the data. Okay, so if you have a better estimation, it gives you a better evaluation. But better yet, you know, as engineers, sometimes we collect data and it doesn't come as a, you know, as a very accurate. So you need to know the range of it. Why? Because once you have the range of the data, you can do analysis over the range of the data, so that you can have the range of the reliability index. Okay, so that's the idea. So what are the information that you need? Again, in the historical data, you can observe the system. Okay, typically what they have in records is the repair time or the reliability analysis. and then they have the failure frequency. So knowing the failure frequency, you can find the mean time between failure, right? Frequency is the reciprocal of that time. And knowing the time of the repair, then you can find the time to fail. And then all of these information you can get. So with just two information, you can get everything. Okay? Failure rate, repair rate, probability, frequency. What they do is they find the average data. Okay? So they look at the failure frequency, repair time, and then they estimate it from the historical by observing the system when it failed, okay? When, and then how long it takes to repair. In the estimation, there are two ways. You do the point estimation, so you have like a single values to represent that's point estimation. Interval estimation is that you have a range of the information on what you're trying to estimate. For the sample means, you have the arithmetic average, and you also have what they call a geometric mean. The geometric mean is help you to take care of the extreme points better. Okay, but when you have the data, you should be careful. You should look at let's say if you have like 1,000 or hundreds compared to the time that you have here, you need to be able to detect the outlier of that data, and then you need to dig deeper and see what happens to that data. Okay, you can't just use the data and blindly just take it. You need to understand where it comes from, whether it makes sense of the data that you collected. Okay. When you have a different groups of data, you might have the weighting average of that. Okay, the weighting average it can be derived from the standard deviation of how the data that you collect has been spread out within the group itself, so that you can have a more representative of the information. So this is just the information. If you get the failure frequency for different groups, you can find the average mean, arithmetic means, or the weighted average. That would represent better. Okay. Not only that, you have the point estimate. You have to look at the interval, which is the confidence interval, and these are what you have in the statistics. Okay, so you just apply what you understand or study in the statistic to help you with the sample average. Okay. Sample average, the sample variance. We will see again the average and the variance when we do the simulation. Okay, and I will also spend maybe half an hour talk about the simulation today as well. Finish this one and then continue with the simulation so that we have enough time to do the quiz next class. Okay. For the sample means, you have the distribution as the T distribution, which is symmetric distribution. I'll just show you that these are the confidence interval of the sample mean. And by central limit theorem, what it means is that the more that you sample, the likely that you get to your estimate true values. Okay. Why is it important? We will do that in the simulation, and we will stop the simulation with a certain when the coefficient of variation is small. Okay, so these are the distribution that they use to do the sample variance. For the probability estimation, so in this case, in some cases, you have the binomial. What does it mean by binomial is that you have only one on or off state. Like in that case, you have up or down, right? So you have like a probability of being up and probability of being down. So you need to, the point estimate is that it's like flipping a coin, the same thing. You flip the coin and then you look whether it's head or tail. If you flip long enough, you will see that the chance that you get heads will be 0.5 and get tail will be 0.5, right? But the question is, when you do the flipping, when do you stop? In this case, you already know that the chance will be 0.5. So you see when it's close to 0.5, you stop. But in reality, in this network, you don't know your true value. So the motivation is how long of the simulation that you should use in order to stop. Okay? By law of large number, when the sample is large, the normal distribution can be used to approximate this kind of binomial, and you can find the confidence interval of this P as well. So of all this, what it says is that if you do if we cannot find the exact value, what is exact value? These are exact value. Through these equations, these are exact value. But for a very big system, we will run the simulation instead. And in those simulations, we don't want to know just the point estimate, just the value itself, but we need to tell the range of it too, whether the range of the estimates that we have is close enough so that we can stop the simulation. That's a motivation of why we need to understand this thing. So now I will introduce you the power system component failure model. Okay. From the beginning of the class until now, it's about lay your fundamentals, get your understanding of the modeling. From now, we will look at how we can use those kind of models that we described and then do the analysis in power systems. So in power systems, as you all know, we have to run power flows, right? In order to understand whether the system can supply the load or not. First, we need to know what is the status of the load. What is the status of the transmission lines? What is the status of the generator? And then once we know the status of each, we run the power flow to make sure that there's a path that it can deliver those power to our end users. If the power flow, solution of the power flow will tell us how much power is injected at each node, how much power is consumed, we already know, right? But the solution of a power flow tell us whether the transmission line is going beyond its capacity or not, whether it will fail or not. Okay, so it's very important that you cannot just take away this power flow from the reliability analysis when you look at the overall system. However, if you look at just one particular area, like in distribution network, in particular one substation, or if you look at just the generator, then you can apply these models and look at that individually. Okay. So what are the basic components in power systems? Of course, you have generators, you have transmission lines, feeders, circuit breakers, transformers, reactors, capacitors. Those are different components. These days you have more and more of the power electronics components in your network. Okay. Those power electronics has different behaviors than these model. So those are something that you need to look into further. I don't think I have those power electronics modeling right here. In the generating unit model, generators are mostly modeled as a 3-state devices, not 2, 3. Okay, we simplify everything by 2 states. Easier, we can understand it. But for the actual system, they use 3 states because sometimes the generator would have the what they call the derated state. It's not the capacity at its full capacity. Okay, so they have this derated state to represent it. And note that all of the generating units, we model it as the steps of the output. As the up state, it's a full capacity. Down state, zero capacity. Derated, partial capacity. Okay. So a two state is a special case when we don't have this derated state. And the unit unavailability, they call it the force outage rate. Okay, force outage rate. So we look at that example. For the transmission lines, they assume two states only. The up state and down state. Up state with full capacity and down state with zero capacity. But then most of the case, the transmission line, they depend on the weather. The failure rates at the normal weather is different from the adverse weather. Okay, repair rate is also different. But this thing, it depends, you know. If you schedule the crew out at the same rate as when it's for normal or adverse weather, the repair rate will be the same. It depends on how you take care of the system. And there would be the average time in the normal and adverse weather. So those average time give us the rates that it changed from the normal weather to adverse weather. The transformer and the bus model, it's the same thing. So they model as a two-state device. And in this case, it's not so affected by the weather. So they assume that there is no weather related in this case. For the circuit breakers, they have three modes of failure. For different modes of failure, they have different models. For the ground faults, they have a two-stage model, like failure, like here, up and down. For the fail to open, sometimes they have like a zone. They look at other equipment as well and look at the effects that cause other equipment. Okay. So sometimes they characterize this failure to open by a probability that it might not respond. And this thing, in that book by Professor Wen-Yun Lee, he will go into the details of the modeling right here. And you can also have the undesired tripping as a failure rate. So, like I mentioned earlier, when you are doing the modeling of these equipment, you need to understand the modes, operation modes of them, and failure modes of them. In reliability analysis, we call it the failure modes and effect analysis. FMEA. And in fact, this kind of FMEA has been used in operations research, in the industrial engineering, in the different field. Because whatever you try to model, you need to truly understand what's going on. Okay? So let's look at the example of the weather-dependent failure of the transmission line. So in the weather-dependent transmission line, you have a transmission line that has 100 megawatt capacity. The failure rate and repair rate depends on the weather. When weather is normal, it has a failure rate of 1 per year. When it's severe, the transmission line has a failure rate 2 times. So it's from 1 per year, it will be 2 per year. The repair rates are the same, which is 24 hours. The average duration in a year of the normal weather is 6 months. So that means that for the adverse weather, it's also 6 months. that gives us the rates of the change. Okay, it will be 1/6 per year, 1.5 per year. That's per month. So what we do is we write the state transition diagram of the system with normal and adverse weather, and write all the transition rates in the diagram. What is given here is that you need to be able to translate the system characteristic and then propose a model for that system. Okay, so if you know that the system behaves like this, how or what is the transition diagram that you should use, and then propose an equivalent model for this system to describe the transfer capability state. What does it mean by transfer capability states? That transmission line can deliver. Transmission line has what? Two capacity, 0 and 1, right? But now, because it has weather, that gives a different failure rate. How can we combine these two to give an equivalent model? What does equivalent model means? Equivalent model means that I can know the transmission line giving 0 at this probability, 100 megawatt at this probability, and the rates between them. Okay, and then you calculate the probability of each transfer capability state as well as equivalent transition rate, and then find the frequency of failure. Okay, so first of all, state transition diagram. This is when the weather is normal. You have the transmission line of 0 to 100, right? And then for the adverse weather, you have a transmission line of going down and to 100. And then creative people like you would also have a question. How come I don't have the transition here and here? Right? What does it mean, transition from 0 to 100 here? What does it mean? It means that, or maybe here and here. It means that I'm here, like I'm from up to down state, but then at that time the weather also changed. Right? That's quite rare, isn't it? Okay, so that's why we only have the transition from the same state. Okay, from the same state. Now, once we have these transition rate diagrams, transition state diagrams, we know that the failure rates is different. From the normal, the failure rate is 1. From the adverse weather, the failure rate is 2 per year. When you work on this problem, try to make sure that you have the same units for everything. Okay, just try to look and recheck that everything is in the same unit. If you use per year, consistently per year. If you use per hour, consistently use per hour. If you use per day, whatever, just be consistent. Okay. The weather transition rate. If you have the transition rate here as per year, the weather should also be in per year. Okay. So if it's per year, it's 2 per year, and also in that case, it's also 2 per year as well, because its duration is 0.5, right? Equivalent model happens when we combine the states 1 and 2, which has the same 100 capacity, and we combine 3 and 4, which has 0 capacity together, so that we can have this equivalent model. Okay, so how do we calculate the probability? Well, this is very easy because it's independent, right? Everything is independent. It's the same thing as in this diagram. There is no transition. Things change state one at a time. So if it's independent, you can calculate it by multiplying the probability of each of the rate. Okay, so you get the probability of 100 and get the probability of 0, and then the equivalent failure rate will become from here the equivalent will be P1 times lambda plus P2 times lambda hash, right? Divided by the probability P1 plus P2. So you get the failure, the equivalent failure rate this much. One thing is that, unfortunately, the numbers here, when we are trying to make the number sensible, the probability of failure is very, very small in terms of, 10 to the minus 3, 10 to the minus 4, 5. So when you work on your calculator, try to adjust it so that you have more of the numbers behind the zero. Try to adjust that. But I'm not going to penalize you for that, okay? But it's just that when you're trying to check your answer, you might see that it's not exactly the same. It's just because of how you use your calculator, okay? So the equivalent repair rate is the same thing. Equivalent repair rate, we calculate it by probability 3 times mu plus probability 4 times mu dash, and then divided by P3 plus P4. Or equivalently, you can also use the same frequency. Okay, it's the same thing. Then divided that, then you get 365. So this gives us the frequency of failure. This gives us the equivalent repair rate and equivalent failure rate. Okay, the frequency of failure is the same as the frequency of success. You can calculate. Frequency of failure is this probability times this rate. Frequency of success is this probability times the repair rate, which will give you the same solution. Okay. So this is all of today's lecture. The takeaways from today is that you have different models. It doesn't have to be just 2 states. It can be 3-state model. You can have more transitions, and with those transitions, it represents what happens in your system. Okay? So if you're using whatever model, you need to ask yourself, can I have the data? Can I represent it using my data? Look at the data first. If it doesn't have it, then you have to collect it. Okay? Build the data. So this is the reference that I use the material from this lecture. Okay, it's by Professor Wenyan Lee. It's called Risk Assessment of Power Systems. For the next, which means now, next lecture, we are talking about the simulation. Okay, why do we do the simulation? Is that you see that when you look at the system, if you were to write down all of the possible states, you have say you have 2 generators, each with 3 states. You have like how much? 3 to the 2, okay. 3 times 3. So you have like 9 states that represent it. Let's see, just 2, maybe 2. So 2 to the 2 will be 4, right? And for the generator, for the transmission line, let me put it right here. Generator in the system, let's say 10. Transmission line in the system, let's say 20. Load in the system, let's say 5. If you were to draw a state transition diagram, how will you able to draw that? How many states are there? Let's say we use only simple 2 states to represent each up and down. So you get 2 to the 10, get 2 to the 20, and if for the load itself, load sometimes it's not even 2 steps, it has like multiple steps, right? So look at these numbers, writing this state transition diagram and using this analytical method doesn't help. So we need to find another method to help us to calculate. What do we want to know? We want to know the probability. We want to know the frequency. These are the 2 index that we need to know, right? How are we going to do that? We need to do what we call it a simulation. It's called Monte Carlo simulation. It's a basic method that mostly used in terms when it comes to simulation. Okay. So the complicating things for the power system is that if you know that generation 1 gives you, let's say it can inject 100, generator 2 can inject 150, let's say just 2, okay? I don't want to write anymore. Transmission 1 and transmission 2, let's say it can give 150, transmission 2 give 100, and then you have the load that can be 50, 100, 150, 200, okay? Let's say you have just this simple, okay, simple. With this simple diagram, you can tell directly if generator is 100, transmission line 100, 150, you can serve the load, right? You can tell it directly from looking at the picture. But what if you have this network and then you have this kind of let's say you have just this bus. You have how many? 1, 2, 3, 4, 5, 6, 7. You have just seven bus. If I tell you that this generator inject 100, let's say this is a generator, 100, this generator of 100, do I know if I get 100 here? By looking at the picture, cannot, right? You can't possibly do that. That's why in terms of reliability, power system reliability analysis, not only that, you need to know the status of each of these components in your system. You also need to know the well-being, how your network perform right here, right? And this is why we need power flow. Okay? And when you do the power flow, it means that you need to know the injections, right? And then you need to know whether it's not overloaded. How it's not overloaded? Because you know the status of each of the transmission line. So you run power flow, and then you find out if there is some loss of flow. And then you collect the data. All of these analysis needs the simulation because you cannot do it analytically. If you do it analytically, it means that you sample the states, you know the probability, but that's not done yet because in this analysis you only know the probability of each state, right? You figure out how many states that will be failure and success. How do you find out? Power flow, right? So that's why you can't escape from doing simulation for this power system reliability analysis. There are two main simulation. We call it the random sampling and the sequential sampling. So let me just I'll give you a bit of the random sampling. Simulation method. Simulation method is supposed to explain next time, but because we wanted to give you, I only have like an hour to do the lecture of that, so that you can have some break, and then you have the quiz. And if we shorten the break, you can have more time for the quiz as well. Okay. So what we do is when we look at the observation of the component, this is how we can extract the information. In this case, you have 3 states, 0 and 1 and 2, and then you wanted to know how long the system stay in 0 state, in 1 state, or in 2 state, so that you can find the rate that it changed. Okay. When you do the analysis, you have to identify all the components in the system to describe the states. And if you look at the probability distribution, you wanted to find out what is the failure probability. And all these, we use Markov model to represent it. That is a component. This is what we study today, right? Component modeling. As for the system, you need to know how it interconnects. If it's just series and parallel, it will be just very easy for you to calculate. But for power systems, it's like all the interconnection, very messy network, right? This is IEEE bus, I think. So this system topology is something that we cannot classify it as series or parallel, simple as that. So we need the further analysis, which is why we need the power flow. Okay. So come back to the same idea. We want to know the ability of the system to perform its intended function. For the case of the reliability, power system reliability is that whether the generator can serve the load. That's the intended function. For the analytical method, we can write, a state space approach. For this simple series system, we can do that. But for a very big system, we need the tools. Okay? So the steps when we use the analytical method is you need to do the matrix inversion. So I'll just give you some concepts of the Monte Carlo simulation. That's all, okay? And then we will solve. I see that you're quite tired. So what it means by Monte Carlo simulation is that you need to sort it out the basic steps first. For the random number generation, it's not relevant anymore because back then, when we studied, there was a random seed, so we need to understand how we get the random numbers. And the random numbers should be truly random in order for our analysis to be correct. But these days, the computers that can run the simulation, they can just give out your random number. So not so much to worry about the random number generation. And then we look at the simulation methods and how we can estimate the reliability. So I just want to show you this picture, okay? What it does is that in the most basic ways, what you're doing is you're constructing the status of the system like this. Okay, so what you do is you look at the status of the component, each of the component through time. When you do simulation, that's what it means. You do it, you sample it, and then you find out, okay, at this sample steps, the states of component A is this much, state of component B is this much, and then you figure out component A and B, the topology, how it looks like, and whether it causes the system to fail. Okay. So that is the how. We need to mimic the failure and repair history of a component, of each component. And from that history, construct the system. How do we construct from this step to this step? You need to know the topology. Okay? And then, if you have the status like here, what you do is you just estimate it using statistical inference, what we had earlier. What is the mean downtime? You observe the system when it's down, and then you add them together. In fact, these simulations right here, it's called sequential simulation because it looks after the time. The simulation goes through time. It's called sequential simulation. For random sampling, there is no time involved. Okay, there is no time involved. So we look at more of the sample, the probability coming out of the probability. So there is no time coming involved. So in the random number generator is the this is how they generate random number, but this is inside the computer that you use. Okay. There are two main simulation methods. The first one, we call it the random sampling or non-sequential, meaning that you sample out from the probability. Okay, from the probability. Remember that we have the discrete time and the continuous time model, right? So you have the transition probability, let's say, and then you also have the transition rates. So for the random sampling, we are sampling from the probability, the probability of the states. State probability. Okay. But for the sequential simulation, we're going to do the sampling based on the rates that it changed states. Okay. Based on the rates that it changed states. And there are two ways to do that, which is like a fixed time. And the next event is that we allow, we find out the time that each of the component will change state. And then we find what is the minimum that it changed states. And then we do the sample out. That would be an example explaining. And after the simulation, we estimate the reliability measure. So we can construct the distribution for some index, okay? Like the mean, the average value. For example, the loss of load probability, the mean cycle time, and the steady state frequency. So these are all the reliability measures that we can calculate. How? What we have is for the steady state probability, when we construct the history of the system, we can calculate, we can find the time that is spent in the success states. We just add up those times and divide by the whole time that we run the simulation. That gives us the probability. Okay, as simple as that. So if you look at this picture of the status of success and failure of the system, in this picture you can use the data that you construct this history to calculate the index, like the probability. You can also find the cycle time. Cycle time is the reciprocal of the frequency. Because you already know the time that it's up and then the time that it's down. So you can calculate this time as well, cycle time. So the steady state frequency will be just the reciprocal of that. Okay. So, okay, I'll just give you some motivations. I will stop it now. What we want to come out from the simulation is we want to construct the system history, okay, in terms of up and down. We want to know the status up and down. How do we do that? We first mimic the history of the component. Each component, find out first what are the states that each component is in, and then use the state to go through the topology. What it means by topology is that you need to find out how it's connected, whether it causes system failure, right? If it's simply connected in series or parallel, it's easy. If it's connected that have a lot of connection, you need to use power flow. Okay. So I think I'm going to stop it now. Any questions about this? Questions about quiz of next week? It would be, the quiz would be about stochastic process and analytical methods. So it would be your homework 3 and 4, okay? Homework 3 and 4. So review that, and you have 1.5 hours. Yes, around that. Okay? Yeah?
Can we use cheat sheet?
Oh yes, of course.
one page, one side of it.
What was that last time? I forgot.
Half
Half page. Okay, you can have one